Let us start with a basic phenomenon of electricity called triboelectric effect, and introduce the concept of electric charge. In everyday life, the amber effect, or more generally the triboelectric effect, is a well-known phenomenon. If we rub a piece of amber with wool, then it will attract small objects, for example paper bits. The word electricus was introduced by William Gilbert, an English physician and physicist, who used the term to describe the amber-like property of bodies after the Greek word electron meaning amber. The triboelectric effect is explained by the presence of electric charge in bodies. When electric charge is present in a body, we say that the body is electrified or it is in a charged state. Our experience also shows that the charged state of bodies remains unaltered in time, and this state is called static electricity. Let us consider two simple experiments demonstrating the basic properties of electric charge in bodies. If we suspend a glass rod through a string or a non-metallic wire and rub it with leather, then the glass rod becomes electrically charged. We can also charge another glass rod by rubbing it with leather and bring near the hanging glass rod. We will see that the two rods repel each other since the hanging rod twists the wire through a given angle, so that the hanging rod turns away from the other one, as the orange arrows show. We can also use ebonite rods instead of the glass rods, but we have to rub them with wool to produce the same effect. The electric charge in each of the rods exerts forces repelling the charge in the other rod, which are indicated with the red arrows. We repeat this experiment, but this time we will bring an ebonite rod near the glass rod suspended through the string. We electrify the hanging glass rod by rubbing it with leather, and we will rub an ebonite rod with wool so that it could also attain charge. If we bring the charged ebonite rod near the charged glass rod, then we will see that the two rods attract each other. That is, the hanging glass rod turns in the direction of the ebonite rod and approaches it. This result demonstrates that the electric charge attained by one of the rod produces a force attracting the charge attained by the other one, and vice versa. We can also perform this experiment several times, when replacing the ebonite rod with other charged bodies. If these bodies are brought near the charged glass rod suspended through a string, they either attract or repel it. This effect is demonstrated when the rod will turn towards or away from the bodies. Then we can conclude from the experiments that electric charge must be different for the glass and the ebonite rods, or generally for two classes of bodies. Benjamin Franklin gave a simple interpretation of this phenomenon. He assumed that there are two types of electric charge, positive and negative. He called the charge of the glass rod rubbed by leather positive, and the charge of the amber or ebonite rod rubbed with wool negative. Based on this interpretation, the experiments show that opposite charges attract each other, while like charges repel each other. If a body is negatively charged, then it repels any negatively charged body and attracts positively charged ones. Similarly, if a body is positively charged, then it repels any positively charged body and attracts the negatively charged ones. If we want to see how the rubbing of bodies helps to electrify bodies, we can make the following simple experiments. Let us charge a glass rod by rubbing it with leather and suspend the charged rod through a string. If we bring the leather near the rubbed glass rod, then the glass rod turns in the direction of the leather, that is, the charged rod and the leather attract each other. Now we can rub the glass rod with leather again and rub an ebonite rod with wool. If we suspend the charged ebonite rod through the string and bring the leather near the rod, then the ebonite rod turns in the direction opposite to the leather, that is, they repel each other. We can conclude from these results that the glass rod attains positive charge and the leather attains negative charge when they are rubbed against each other. In generally, if we rub two bodies against each other which are made of different materials, then the bodies attain the opposite charges. Therefore, the rubbing does not create any charge but separates opposite charges in bodies. Actually, we can check whether the rubbing of bodies is really needed for the separation of charge in them. Let us rub a glass rod with leather and an ebonite rod with fur or wool. Then the glass rod attains positive charge and the ebonite rod attains negative charge, which are represented with the red positive signs and the blue negative signs respectively. If we have two pith balls suspended through strings, though we can touch one of them with the charged glass rod and the other one with the charged ebonite rod. If we remove the rods, we see that the pith balls move towards each other, which indicates that they attract each other. This means there are attractive forces between the pith balls. We can interpret this effect in the following way. When the pith balls are touched with the oppositely charged rods, they obtain positive and negative charges respectively. Then the electric charge can be transferred by contact. Rubbing of the bodies helps us to separate charge in them since it makes the transfer of charge between the bodies more efficient. However, rubbing is not necessary for the separation of charge. We have seen that different materials attain different types of charge, due to contact or friction. Therefore, the behavior of bodies related to the separation of charge depends on their material properties. Let us examine this dependence in the following experiments. If we hold a metal rod in our hand and rub it with wool, then the rod will not attain charge. However, if the metal rod has a glass or plastic handle, then the rod can attain charge after being rubbed with wool. A charged metal rod will lose its charge if we grasp or even touch it with our hand. It is not the case for a charged amber or glass rod. They lose their charge only at that part where they were touched. Based on such a behavior of the different materials, we can divide them into two classes. The first one is the class of conductors, and the second one is the class of insulators. In conductors, electric charge can move and propagate fast. Typical examples for conductors are metals, the human body itself, or simply the ground. Therefore, we can use metal wires to transfer electric charges from a charged body to the ground. As opposed to the conductors, electric charge cannot move in insulators. Such materials are, for example, glass, ebonite, or amber. It is important to note that perfect conductors do not exist. Even if metals are very good conductors, they are not perfect ones. As a result, the border between conductors and insulators is not sharp. We have seen that rubbing bodies against each other brings them into a charged state. In electrostatic, several simple methods have been invented to determine whether a body is in a charged state, that is, whether it attained charge. There are measuring devices called electroscopes, which are able to show the presence of electric charge in bodies. One of the simplest electroscope is the gold leaf electroscope constructed by Abraham Bennett, an English clergyman and physicist in 1787. He used this instrument in many simple experiments, when he studied the basic phenomena of static electricity. In the photo, we can see a gold leaf electroscope with a glass metal case. It consists of a disc called charging plate, which is attached to the top of a vertical metal rod. The rod is normally made of brass, and golden leaves are attached to its lower end. The lower part of the metal rod is encased in the glass metal box insulated from the rod. If a charged body touches the charging plate, then the gold leaves spread apart since the parallel strips with the same type of charge repel each other. The angle between the two golden leaves is proportional to the pair of forces pushing the leaves away from each other. The force is proportional to the amount of electric charge distributed on the surfaces of the leaves. This amount of charge is proportional to the charge transferred from the glass rod, that is the charge of the body touching the plate of the electroscope. The angle between the golden leaves proportional to the original amount of charge of the body. The more the stripes diverge, the greater the amount of the charge in the body is. Then we conclude that the position of the golden leaves in the electroscope indicates the amount of charge of the bodies, which provides a rough measurement of charge. Another type of the electroscopes is the pointer electroscope, which allows us to have a more quantitative description of the amount of charge in bodies. It consists of a charging plate connected to a support stand extending through the center of an insulator scope. A needle rests upon the support stand which can rotate about its pivot. The plate, the stand and the needle are made of a conducting material. If a charged body touches the charging plate, then the support stand and the needle attain like charges and they repel each other. Then the needle will rotate around its pivot until it restores the balance. The rotation angle is proportional to the forces acting between the needle and the support stand. The forces are proportional to the amount of the electric charge distributed on the surfaces of the needle and the stand. This amount of charge is proportional to the charge attained from the glass rod touching the plate. Then we can conclude that the rotation angle of the needle is proportional to the amount of charge attained from the charged body brought in contact with the plate of the electroscope. We can use the golden leaf electroscope to classify different materials as electric conductors or insulators. If we have the same type of electroscopes denoted with the letters A and B, and we charge or electrify the electroscope B, then its gold leaves will spread apart, indicating the presence of charge on the surface of the leaves. Let us connect the charging plates of the electroscopes with a metal wire. Then we will see that the leaves of the electroscope A diverge while the leaves of the electroscope B becomes more relaxed. However, if we connect the charging plates of the electroscopes with a glass rod, then the gold leaves of the electroscopes remain in the same position, indicating that there is no charge transfer between the devices. These experiments demonstrate the following simple facts. In conductors, the charge carriers can move, which allows charge transfer between bodies by using such materials. This was shown in the first experiment, where we could transfer charge between the electroscopes through the metal wire. In insulators, the charge carriers cannot move, which prevents us from transferring charge by using such materials. This could be seen in the second experiment, where the glass rod connecting the charging plates of the electroscopes did not allow the charge to transfer between them. Now let us consider the following experiments demonstrating the transfer of charge between bodies, and presenting how gradual charging of bodies works. We use a simple setup, where a metal ball is hanging on a string. First, we electrify a glass rod so that it could attain charge. Then we touch the metal ball with the charged glass rod, which allows us to transfer some charge from the rod to the ball. This charge transfer can be demonstrated if we bring the metal ball into contact with the charging plate of an electroscope. We will see that the gold leaves of the electroscope diverge. Since some charge is transferred from the metal ball to the electroscope, the ball lost that amount of charge. We can recharge the metal ball by touching it with the charged glass rod. If we bring the metal ball into contact with the charging plate of the same electroscope again, then the gold leaves of the electroscope rise further. This result indicates that more charge was transferred from the ball to the electroscope, which has an important consequence. With repetition of these steps, we can gradually charge the electroscope, or any other object. By using the same experiment setup, we can also discharge bodies, and demonstrate the neutralization of opposite charges. First, we charge an ebonite rod and touch the charge-free metal ball with it. As a result, we have transferred negative charge from the rod to the ball. Then we bring the metal ball into contact with the charging plate of the electroscope, which was electrified with positive charge from the previous experiment. If the metal ball and the instrument get into contact, then the deflection of the gold leaves will decrease. We can recharge the metal ball by touching it with the charged ebonite rod. If we bring the recharged ball into contact with the charging plate of the electroscope, then the gold leaves become even more relaxed. This result indicates that we remove charge from the electroscope, which is the neutralization of a charged body. By repeating this process several times, we can gradually discharge the electroscope or any charged object. We can also use the electroscope in the experiments, where we study the separation of opposite charges by friction. If we rub a paraffin wax bar against the charging plate of an electroscope, and remove the paraffin wax bar from the plate, then the gold leaves of the electroscope will rise. If we touch the charging plate with the paraffin wax bar again, the gold leaves will relax. We can interpret this result in the following way. The same amount of positive and negative charges are separated in the bar in the electroscope by rubbing them against each other. Then the same amount of positive and negative charges are neutralized in the bar in the electroscope by bringing them into contact with each other again. We have already seen that we can separate positive and negative charges in bodies if we rub them against each other. Now we can ask what will happen if we just bring the charged bodies near the electroscope. In the first experiment, we use a positively charged electroscope, where the separated gold leaves indicates the positive surface charge on the leaves. If we bring a positively charged glass rod near the charging plate of the electroscope, then the gold leaves rise further. If we remove the rod from the vicinity of the plate, the gold leaves take their original position. In the second experiment, we can also bring a negatively charged ebonite rod near the charging plate of the positively charged electroscope. Then the gold leaves of the electroscope become more relaxed. If we remove the rod from the vicinity of the plate, the gold leaves rise to their original positions. The interpretation of these results is the following. If two charged bodies only approach each other, then the charge separation can already be measured in the bodies. In the first experiment, the positive charges repel each other in the bar and the electroscope, reducing the surface charge on the plate of the measuring device and increasing it on the gold leaves. In the second experiment, the negative and positive charges in the bar and the electroscope attract each other, increasing the surface charge on the plate of the electroscope and decreasing it on the gold leaves. Therefore, we can determine the type of charge in a body without bringing it into contact with the electroscope. Let us study the separation of the positive and negative charges in greater detail. If we rub bodies against each other, we can separate the positive charge from the negative one in bodies. As already mentioned, the friction between the surfaces of the bodies helps the separation. However, this separation can be done by the effect of separation of charge without bringing the bodies into contact. This effect will be demonstrated in the following experiment. We use two electrically neutral metal cylinders denoted by A and B, which are brought into contact with each other. Both cylinders are mounted on stands made of some insulating material. First, we bring a negatively charged ebonite rod near the cylinder A, and move the cylinders away from each other while we keep the ebonite rod close to the cylinder A. Then we remove the ebonite rod and determine the types of charge in the cylinders with an electroscope. We find that the cylinder A has positive charge and the cylinder B has -1. This effect is the separation of charge in the two cylinders. After having brought the charged cylinders into contact with each other, we find that the cylinders become electrically neutral again. We can give the following explanation for the separation of charge demonstrated in this experiment. In the natural electric state, conductors contain the same amount of positive and negative charges, which are evenly distributed in the conducting body. As a result, the entire conductor is electrically neutral. In the vicinity of a charged body, there is a charge separation in the conductor. If a body near the conductor has negative charge, then this charge attracts the positive charge and repels the -1 in the conductor. In the part of conducting material that is close to the negatively charged body, the positive charge will be abundant. On the opposite side of the conductor, there will be an excess in the negative charge. This is the effect of the charge separation in a conductor. If we remove the charged body from the vicinity of the conductor, then the even distribution of charge will be restored in the conducting material and becomes electrically neutral. The electric charge induced by the separation of charge is called induced electric charge. Let us consider the following experiment related to the induced charge and the concept of ground in electrostatics. In this experiment setup, we use a grounded metal cylinder, that is a conducting body connected with the ground through a metal wire. First, we bring a negatively charged ebonite rod near the grounded metal cylinder. If we remove the ebonite rod and disconnect the cylinder from the ground, we find that the cylinder is positively charged. The explanation of this result is simple. The negatively charged ebonite rod brought near the cylinder attracts the positive charge and repels the -1 in the conducting body. The left-hand side of the cylinder is closer to the rod and it will be abundant in induced positive charge. The right-hand side is far from the rod and it will attain more induced negative charge. Since the right-hand side of the cylinder is connected to the ground, negative charge flows from the cylinder to the ground through the wire. The charge transfer causes shortage in the negative charge in the cylinder. If we remove the ebonite rod and disconnect the ground, the separation of charge will cease in the cylinder and the charge becomes evenly distributed in it. Since some amount of negative charge was already removed from the cylinder, its net charge will be positive. This experiment demonstrates that the ground or the earth behaves as an electric reservoir with a vast capacity. Theoretically, it can attain or supply an infinite amount of charge without being in a charged state. As a result, we can transfer an arbitrary amount of negative or positive charge between any object and the ground if we bring them into contact. The photo shows a building grounded to the earth for safety reason. Since the capacity of the ground is huge, it can be used to dissipate the great amount of charge from the lightning strike through the lightning rod connected to the ground. This application demonstrates that the grounding system of the earth provides a good protection of any device from electric shocks. The ground symbol indicates on any instrument or any object that it is grounded or connected to the grounding system.